Simple RAG breaks in production. In this video, we'll see why and how to fix it. I'll cover 3 critical solutions. 1. Chunking strategies that actually preserve context. 2. Query understanding beyond basic similarity search. And 3. Hybrid retrieval systems that combine multiple search methodologies. This video assumes that you know basic RAG, although we'll do a quick 2-minute recap and then dive into production grade solutions. If you're building RAG applications for real systems and not just demos, this video is for you. On your screen, you can see the simple version of a RAG. I call it the naive version of the RAG that became popular in 2023. This is an architectural pattern. We won't get into the details of it. You can see there are lots of videos available online or even blogs or tutorials on it. We will quickly recap this version and then move on to the more advanced version of it. On the left, you can see in the data preparation phase that happens offline is collect data from different data sources, extract information, clean it up, and then transform the data into embeddings using fixed length chunks. So the data is taken and divided into fixed length chunks and sent to the embedding algorithm, which would then transform the chunks into single vector embedding per chunk and stores the information in the vector database. What happens online is the user asks the query from the application, which gets converted into an embedding, and then you find the chunks that are the most similar to that embedding, send the retrieved information to the language model, which then transforms into the usable version or the response version to the user by reformatting the retrieved data and making sense of that data. There's several problems with this version of RAG. We'll discuss 3 of them in this video. First problem is fragmented context. What I mean by that? So basically, when you prepare the data on this side, you collect different data sources, you extract information, do some processing, and then divide the information into different chunks. And then you embed that information in digital format and store it in the vector database. When we do the chunking in data preparation phase, if we do follow the fixed chunking approach, for example, if this is my document, in the fixed chunking approach, the document is divided into fixed length chunks. What it does is when it saves these chunks in different embeddings into the vector database, the biggest problem is it treats different chunks as separate, independent knowledge. However, the real knowledge is not fragmented. It's highly interconnected, it's contextual, and it's hierarchical. And I'll explain in a minute what I mean by that. Let's see an example here. This is my document of, let's say, a remote work policy document that I'm trying to save in my vector store. If I follow the fixed chunk approach from 2023, what I would do is, if I decide, let's say, a fixed length of 30 tokens or 30 words. In that case, I will just divide this arbitrarily on the basis of the length. Here, I would divide here, I would divide here, I would divide here, and so on. And these are all chunks with a length of 30 that is pre-decided when I'm trying to divide this information into the chunks. Now, what's the problem with this? The problem is that when I try to retrieve it in the retrieval stage, this chunk might be extracted in an answer to a question. This chunk might be extracted. And let's say I retrieve 3 chunks. One other chunk would be, let's say I extract this particular chunk from here to here. Now what happens is this chunk does not contain the entire information on its own. Its main information lies in this chunk, which is being left out. When I extract this chunk, for example, the information is also available in this chunk that is relevant, may not be picked up. So, what I mean by that is the fixed chunk approach treats different chunks as independent. However, the information in this document is highly interconnected. You do need, for example, if you need to find out the eligibility of remote work in this case, you need eligibility as well as alternative options that are available in these chunks, which might not be picked up in this simple approach. To solve it, what people did was they kind of decided to overlap these chunks. So instead of just making these chunks independent, they just try to find overlapping chunks. For example, the first chunk is this, the second chunk instead of that is more like it starts here and ends here. So now you have an overlapping chunks. Even this does not solve the problem, because even then you might miss out on a lot of information. Even if the chunks are overlapping, it doesn't solve the problem completely. How do we solve it? In the modern version of RAG, how we go about solving these kind of problems is with the help of, let's go back to the original diagram. So yes, so one, we do something known as a semantic chunking with hierarchies. Second, what we do is we improve the embeddings, this stage. So let's talk about what happens in semantic chunking with hierarchies and how we improve the embeddings. Let's get back to our original example. So now, instead of fixed length chunks overlapping or not, I would try to store this information as in hierarchies and in semantic way. In semantic chunking, what happens is you take a particular section, consider that as one semantic boundary, and divide the chunks in that manner. So here the top section, the remote work policy, and then eligibility requirements could be one section, one chunk. The second chunk could be the work arrangement options, first option, and then the third chunk could be the third option, and so on. So now, instead of arbitrary boundaries, we have well-defined boundaries as semantically defined by the document structure. Instead of, in addition to semantic, we do hierarchical chunking. How we go about it? So here there's a certain hierarchy in the data. For example, the top hierarchy is remote work policy, is a document. Then you have 1, then you have 1.1 and 1.2 and so on. Then you have 2 parallel to 1, and then the hierarchy is like 2.1, 2.2, 2.3. This is kind of inherent parent sibling relationships. For example, 1, 2, 3, these could be parent siblings of each other, and they could be parent of their subtext. For example, 2.1, 2.2 can be children of point number 2. So there's parent-children relationship, and there's a sibling relationship in the document. That's called a hierarchical manner. How we implement this in practice? How we implement this is we would, for example, my chunk 1 would be something like this. It has, this is, let's say, my vector store. How we store this chunk in this vector store is, first, it would have the text. Let's say this is my text of this chunk. Then it would extract more information. For example, it could say that this is the 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 title of the chunk is, let's say, exception to the policy. Exception. So we try to extract entities like title and other entities from this chunk that could be semantically valuable to us when we are trying to extract or retrieve information from the vector store. Another information that I would store in vector store is, as previously mentioned, embedding. And then for the hierarchies, what I'll do is write parent as one of the fields, and write, let's say, section, this is section number C1, its parent would be C in the document. Or if it's, for example, if it's, could be anything, depends on your document, 1.1, and this parent could be 1. And siblings could be 1.1, 1.2, 1.3, and so on. So this is how I would store this particular chunk in my vector store in key value format with name, text, other semantic entities like title, subtitles, what are the, basically try to extract information from the chunk in a manner that could be more helpful. Then with the embedding, parents, and siblings. How this helps is, let's say this chunk is a match when I'm trying to retrieve the information. What it would do is it would look at the parent and look at the siblings as well to enhance the context for my language model. So it would not only look at this particular chunk, it would also look at its siblings, 1.2, 1.3, and so on. It would also look at maybe the parent, depending on how we define it. This solves the problem of interconnectivity and context fragmentation in my simple RAG by enhancing it. One more thing that it does is in the field of embeddings. So when we are talking about simple RAG, we know that one chunk has a single vector embedding. For example, chunk 1 could have an embedding called single vector embedding, maybe 728 dimensional, let's say 0.1, 0.2, something. Now this is single dimension embedding. It doesn't capture all of the information in that chunk. We use some sentence embedding method like sentence BERT, for example. To enhance this embedding, we would use multi-vector embeddings in modern RAG. How it would look like is, for every single token, we have one vector. Let's see. So here, in the embeddings field, we could have something like, instead of the previous single vector, 728 dimensional, instead of that, we could have this single vector corresponding to one token. So this key value of embedding could look like embedding, and then there's another key value. Keys are the specific tokens. For example, in my text, the officer can do. For example, this is my chunk text. So it would kind of, for every token, there is one embedding. And this one embedding is, a single vector corresponding to that. So basically what we're trying to do is converting the previous method of a single vector embedding into multi-vector embedding, one vector corresponding to one single token. This captures additional information because in sentence embedding, we lose out on a lot of information. The greater the dimension, the greater the level of embeddings that we go to, from single to multi-level or multi-vector embeddings, the more information we can capture from our chunk. So that's how we are capturing additional information from that one chunk by going to the token level and capturing token level single vector embedding. So this solves all the problems that we discussed with that we found with chunking, in that the knowledge is hierarchical, contextual, and interconnected. It's not fragmented, and with the help of these additional changes in the modern RAG, now this has improved our architecture by a lot, because now we are able to capture interconnections with the help of semantic similarity, semantic chunking, hierarchical chunking, and then we are improving the embeddings as well. So by improving these two areas, our document processing has become much better. In the previous section, we discussed the chunking and embedding issues with the simple version of RAG, and discussed how we can solve it in the production version of RAG. Now, moving on to the second problem with simple version of RAG from 2023. This is about query understanding. In the right side of your diagram on the flow chart, you can see that as the user sends query to the application in the simple version of RAG architectural pattern, the query gets converted into a one single vector embedding, and that gets sent to the vector database, finds similar chunks, retrieves similar chunks, and then sends it to the language model to process and return the response to the user. Let's see what are the problems with this approach with the help of an example. Right. So in this version of the naive version, as I call it, of a RAG, you can see that user sends a query, can I take time off next week for my wedding? This goes through the embedding, and the embedding vector looks like this, and then it sends to find the cosine similarity search in vector database to find top 5 chunks as per the setting, and then this response is sent through a language model, a small or large language model, and the system response. You can see in the diagram, in the flow chart, that your top 5 results that you see are highly irrelevant. For example, the user is asking, can I take time off next week for my wedding? The results are from the documents such as wedding vendor discount program, which is highly irrelevant. The only relevant part here is the point number 4, personal leave policy section, which is not in the top 1 or top 3 chunks, it's on the 4th position. This shows us that retrieval of an information pertaining to the right user query did not work as well as we had hoped. So how would the response look like? The response looks like, based on the employee benefits, the company offers various time off options. Not exactly as you had hoped. You can also track your time using the time tracking software. It's highly irrelevant. You can see the problems with this, right? The response is highly irrelevant to the user query. It looks like the system did not, the algorithm was not able to get the intent of the user, which was to find the procedure document that would help the user identify what are the options to take the time off. So first is highly irrelevant, second is intent understanding. Third problem with which I can see in this response is that the system was probably not able to identify that it was a urgent request. So timeline, it has to be the next week. It was not able to identify anything that is pertaining to an urgent request, or so basically context related to time or urgency. Fourth thing is that it seems like the search results are highly impersonal. They are not pertaining to this particular user. And moreover, we can see that there could be other discussions going on in this session, which this cosine similarity search hasn't been able to account for. How to solve this? So to solve this thing, basically we can see how we can solve this situation in the newest production level RAG. We can solve this with the help of enhanced context. First, we'll add user context. So things related to the user, like the user is the employee, the department of the user, employment time, and so on. We will extract the query details, like the intent of the query. Here it's time off, it's urgent, combines those two things into the intent, primary as well as secondary intent. It also tries to extract the entities from the user query so that the the retrieval algorithm can be very clear on what exactly is the action needed, what is the timeline look like, what's the intent of the user, and what exactly are they talking about. Then the event type, urgency level, and so on. You can add more details here in these context types as per your need. Try and test with different things. Like, for example, you can also test out more details. Like, you can test out the session details. What are the other discussions going on in the session? So, session history. You can add more details related to the environment. Like, for example, the employee is based out of the US, the employee is based out of another location. These things will enhance your context. So we combine these different types of context and send the resulting combine all of them into a combined context. It might look like this, it might look like something else for your case, but it's just an example to show that how we try to enhance the query right after the user sends the query, enhance it with the help of user context, extract the entities, extract the intent, extract the details regarding the environment, the session, and so on, and combine into a single context. This greatly enhances your query, adds context to it, so that the problem of query not being able to understand the query by the algorithm is solved. Next thing that we do here is called knowledge orchestration. Let's talk about it. So we discussed query understanding. The next step is knowledge orchestration. So we saw that we combined extracted user context, we extracted the query context and any other context needed. We combine all of these details into a combined context and send it to the knowledge orchestration. The knowledge orchestration is nothing but a mechanism to plan the next step. There are several planning activities that are possible, but in our case, we can see that in this case, it will be useful to understand the permission of the user. For example, does this user have access to the documents that we are trying to extract or retrieve from the vector store? So that would be one. Second would be how fresh the data has to be. In this case, it's very important that we capture the data or retrieve the data that is more recent. Otherwise, if we cannot do this, if we cannot grab the latest information, then maybe the policy document from 4 years ago is extracted and that information is not relevant on the present date. So it's very important to understand how to plan out the information retrieval from the vector store. For that, these three are just simple examples of the kind of planning activities that might be important. Second one was a freshness requirement, and third is retrieval strategy planning. So basically combining all of the permission, freshness, and then combining them with what exactly is the best approach to go about it pertaining to the user query and the user details. Basically the combined context. Why we need this knowledge orchestration is because the step in which we are planning the document retrieval or the information retrieval has to be very specific to a particular context. In a different context, in a completely different context of this RAG architecture, we might need a different planning approach. We might not need permission, for example, in that case. We might not need fresh information in that case. So it's very context dependent. By context, I mean the combined context that we extracted. And this combined context, just for a review, was What exactly is the query asking for? So the intent, entities, timeline, urgency, user details, etc. This is how, if we include the steps of query understanding as well as knowledge orchestration, it can really help our accuracy of the results and relevance of the results. So, coming back to my original diagram, original flow chart. So, in the previous section, we solved the problem of chunking and embeddings. In this section, we solved the problem of query understanding and knowledge extraction. Sorry, knowledge orchestration. The third issue with simple version of the RAG is in the knowledge retrieval stage, which happens in this part. In the simple version of RAG, what happens is the query is enhanced, as we discussed, with the help of query understanding and knowledge orchestration. It goes through the embedding stage, in which it's converted into a simple single vector embedding with an algorithm like BERT or sentence BERT. And it tries to extract fixed chunks, n number of chunks. It could be n, could be anything, 5, 10, any number of chunks that are similar to the query, with, and the similarity is found with something like cosine similarity, to find top n number of chunks. Those are retrieved and sent to the language model. That, combined with user query, is sent out as a response to the user by the language model. This is how it was done in the simple version. And it doesn't perform as well. Why? We discussed the problem with different chunks. To enhance this, we do intelligent retrieval. Let's talk about how this advanced or production version of retrieval works, which we call enhanced or intelligent retrieval method. Sorry, my bad. Clearing up the diagram. So how this intelligent retrieval works? How this intelligent retrieval works is it takes a query from here, the query, enhanced query that passes through knowledge orchestration, with enhanced context. It takes the query, and instead of passing it through the vectors database to extract top n number of chunks, it'll go through 3 parallel ways of extracting information. These 3 parallel ways would be: 1, the similarity search from vector store, that similar to how it happened in naive version of a RAG. The second would be these 3 parallel methods, right? The second would be our retrieval from something known as a document store, and this is text similarity. So you know that we store all the data in vector database, correct? In the form of vectorized representation of all the knowledge extracted in different chunks, converted to embeddings and stored in the vector database, correct? Now, in addition to this vector database, we also store our information in knowledge or document store, as well as a graph store in, in some sort of graph database like Neo4j. So now in the retrieval stage, we search information not only from the vector store, but also from document store and graph storage. So what kind of information is stored and what algorithms are used to extract this information, to retrieve this information, right? Vector store, you know, it stores vector, multidimensional vectors. It could be simple vectors like BERT, sentence BERT, or it could be multi-vector embeddings like Colbert. It's exactly similar as what happens in a simple RAG. Document store actually stores all the documents along with a lot of metadata. So let's say you store information in different chunks in the vector store, but you in document store you store all the documents that you retrieve. So it's kind of a very big database, and you use some keyword matching algorithm to extract information from it. So you don't really use digital method or formula to extract information. You use something known as BM25, which is a type of TF-IDF, term frequency inverse documents frequency kind of method, as well as you use SPLADE. These two are a kind of modern approach. And BM25 was an old approach. SPLADE is a modern approach for text matching to find the relevant documents. And the third is graph algorithm. So you use graph, the knowledge graph algorithms are kind of advanced algorithms in which you find all the entities related to a particular entity. By entity, I mean any tokens, any concepts. For example, let's say car is a concept, car company, let's say let's say Ford Motors, or let's say Tesla is a concept. These are interconnected entities, right? So that's how we find interconnected entities using graph-based algorithm from a knowledge graph. And this works in parallel to the other two methods that we discussed to grab the top documents or top chunks that contain the relevant information to answer to our user. And then in the right after these algorithms work in parallel to extract relevant information from vector store, from document store, and then from the knowledge graph database. How do we combine these to get the top n documents? So there's something known as a fusion ranking algorithm, and one of the top fusion ranking algorithms is reciprocal ranking fusion, or reciprocal fusion rank. Reciprocal fusion rank algorithm. How it works is it takes the ranking of all three by all three, and then combines them in a way that they can find the final ranking of every single document that goes into that's the final answer that is sent to the language model, and that's how the response is sent to the user by the language model. What's the typical formula of this reciprocal fusion ranking algorithm is, let's say you have ranking of document 1, document 2, document 3, like this, from vector store. From document store ranking, you find that your ranking looks like this. Top D1, D2, and so on. So how you would work is you would combine the ranking of every single document in different algorithms and sum them up to find the ranking of a particular doc. So for, let's say, document number 1, you would take the ranking of document 1 in the first algorithm, which was 1. So you would do 1 upon 1 plus 60. So 60 is kind of an arbitrary or a number that is a constant. You can change it, but empirically it has been proven that 60 works well. So this is the ranking in doc number I, sorry, in algorithm number I, and it works across different algorithms. So in our case, the rank of, let's say, this document 1 would be a sum of ranking of document 1 in first algorithm, which was 1, plus 60, plus 1 upon ranking of document 1 in algorithm number 2, which is 2. Its position is 2. So it will be 2 plus 60. And I'm guessing in the third algorithm, which was my graph algorithm, its ranking, let's say, is 35. So 35 plus 60. In my case, let's say its ranking is, since there are only 3 documents, let's say its ranking is 3. So this formula will give me the ranking or a score for document number 1. I'll find the score for document number 2 and document number 3, and in the order of highest to lowest, I will sort my documents, and that would be my final ranking. And that's how top documents are found and sent to the language model, and via language model sent as a response to the user. This is called intelligent retrieval process, and I would say combining these 3 advanced methods is standard in top companies. In several of the top companies are applying these methods to enhance the performance of a simple RAG into kind of a production version or a more modern version in September 2025. So if I go back to my original example, can I take time off next week? If we apply all the techniques like multi-vector embedding instead of a single vector embedding as we have here. So we apply multi-vector embedding, and we apply query understanding and knowledge orchestration, and we apply knowledge retrieval. If we apply 3 improvements in our naive version of RAG, we can reach a very good response. For example, you can see the difference between the 2 responses. This should be not naive, this should be the production version, right? So you can see that the quality of the system response, the accuracy, and the relevance of the system response has been highly increased if we apply these 3 changes to naive RAG to convert it into a production version of RAG. And I would encourage you to apply these advanced methods in your production version of RAG. Try them out. Let me know how it works.